Hi everyone, technology check. Can you see and hear me? Please indicate this topic. And the next topic is that we are covering right now. So we're switching to the lecture now. Please stay focused. Okay, we are continuing linear models. Well, we are only working actually with linear models in this course. This is the classic way of studying time series. Non-linearity is a very special topic, and it's studied only in special topics of time series that in no way can fit into a basic course. But we are working still with univariate linear models, and next week we are going to discuss multivariate models for some time. This is the last part of the material in the course that is going to be relevant for your project task also. The next part, the next topic is only going to be present in the classes and in the exam. So this is the last portion of what you are going to do also in your project tasks, the prediction part. Some of you already started, and on Sunday I will answer all your reports and make comments, and you can combine those comments with the knowledge that you gain today and tomorrow in the practice sessions. Yes, this week there are practice sessions as usually. We're going to discuss the quiz that you did just now and the prediction. So you can combine those knowledge together and finish your projects. You have a couple more weeks for that. So while you are working, continue working on your project, please stay in connection with me, ask questions, and follow my comments. That would be enough. Now we have to finish the univariate linear modeling, and the question is here, so another question, or the one that we already answered, but this is the transition point. Why do we need ARMAs? We know why we use ARMAs, why ARMAs models are important. You just answered those questions, because basically any stationary process can be represented by some ARMA process. This is both a theoretical result and it has a practical empirical approach, the Box-Jenkins approach behind it. So why do we need it? Well, first of all, of course, there are some theoretical insights or some insights about the data that we can get from using ARMA process to describe data. This is some explanations about nonlinearity, the degree of dependence, how well the representation can be, and so on. Something more about stationarity of the process, how close the process is to a unit root, for example, and so on. And then, of course, there's other purpose to use ARMAs, and this is more popular though than just modeling, but still the idea is the same, that we can use a bunch of ARMA models of some order, not too high, to extract that linear component from the stationary time series, and the rest of it is weak white noise. And weak white noise is something quite simple, well, not so simple, but something that is very useful when we see it in real life. It is never that we see it in actual data, almost never, but we can see it as part of our model, some component that can no further be explained. It's something like a random error term, not completely random, because they can be still there can be still some dependence between the current values and the future values of weak white noise, because it's weak. Yeah, it's still, there is some dependence, but it is at least uncorrelated, and it means that in terms of linear models, there's no something like linear dependence, or there sometimes uncorrelatedness is called or interpreted as linear independence. In terms of linear models, we cannot further explain weak white noise or predict weak white noise, and it means that well, we can use that linear component that we extracted in form of ARMA process to actually predict the future values, because the required noise on average, or in expectation, in theory in expectation, in sample on average is 0. So whatever is going on in the data and described by the stationary linear ARMA representation is going to predict the future dynamics of our stationary data, or stationary process. So this is what we are covering now. There's some terminology mix-up in this lecture, and overall, this is intentional in this lecture, because there is overall also some mix-up of terminology in the prediction and forecasting literature that is related to time series or not to time series. I'm sorry, this we don't need now. Can you still hear and see me?
Передал, но на секунд 5 скралась звука и изображения.
Yeah, yes, thanks. By the way, everyone that is now following me in the Zoom meeting, please type something in the chat, like click, just send a plus there, or write that I am here. This is just a minor check. Mm-hmm. Yeah, so everyone keep doing that. Not repeatedly, but until everyone has done it. Yeah. So hopefully we didn't miss anything. So there's a mix-up in terminology in the general prediction terminology, or general prediction literature and textbooks and courses and forecasting, about what is the right term to use for that. Because in this lecture I am using both terms. You saw that there's, sorry, terms predicting and prediction here. So that's what we are going to do: prediction, predicting, prediction. But in a few slides, or like even right now, you will see that there's going to be a substitution of the term prediction with the term forecast. And I'm using intentionally term prediction in the beginning, and then I switch to forecasting. And in the classes and in your projects, you can use both, because in this course they are interchangeable. If you go to this link here, this is just, I quoted as a source of this picture that I used, but there's also an article, something like data science related article, about whether we can substitute or interchange the words forecast and prediction, and there's a nice explanation why not. But actually in this course, yes, we can, because this course is solely about time series, and in case of time series and predicting future values based on the past values is actually what is called forecasting. So forecasting is something a more narrow term than prediction when we are talking about time series especially. Sometimes forecasting can be more general than prediction, but we are not going to touch that at all. So in our course, it is okay to interchange those terms. In general, of course not. But in Russian language, the situation is almost the same, even though there is more flexibility about that. The prediction would be прогнозирование, I think is the most accurate term. Forecasting would be предсказание. And in academic literature, in academic context, we never use предсказание, even though forecasting is a legit term in the field and in the literature about time series prediction. There are even journals that are specializing in forecasting. That means predicting future based on past or current values, or some models that are based on the past data. Okay, we're starting instead of getting to theory, we are starting from a very simple example, because this is what we are going to discuss: prediction and forecasting based on a linear models that we study. So imagine that there is a process that is, well, in this case, an autoregressive of order 1, and it is a complete process, so there's a whole description of it, including the weak white noise. And currently it's time period t, so this is what happened. We are now at time period t, or we could call it like t naught or something like that. And the current value xt is 1.2. So this is what we have. This is the information we get. Then there are a few questions. So what is the expected value of xt plus 1? This is a very easy question. You are able to calculate it yourself, actually, very quickly. Can anyone tell really quickly what's the expected value of xt plus 1?
Это при условии, что XT 1,2, да?
No. What you are referring to would be conditional expected value, and this is just expected value. So this is what it is. And this is absolutely right, this question that you asked. So, and yeah, no, it's not conditional. Why 1.2? That's a strange thing to see here.
Ну, один вроде.
Yeah, so the expected value of a stationary time series process, and we know that this autoregressive process is stationary because this is an autoregressive process of order 1. The autoregressive coefficient is less than 1, strictly less than 1 in absolute value, this 0.25. It means that the process is stationary, and this expected value is constant over time and is defined, and we can even calculate it. If it was something else like unit root process with 1 plus 1 or minus 1 here, or something explosive with more than 1 in absolute value, this coefficient, then we say, okay, so the expected value is still defined, but we cannot find it because it changes over time. It's not constant, no way we can see. But for a stationary process, yes, we can, and for autoregressive of order 1, the rule is like this. So yeah, it's exactly 1. This is the expected value. And the next question is naturally, yeah, well, but what if we are interested in the expected value given that we know some information about the current value? So what is the expected value of xt plus 1 given that the current value or the closest known value of the process is 1.2? This would be the conditional expectation.
Ну, 1,5.
Why? So yeah, it's something different. The general rule of finding this kind of expectation is that whatever is in the condition we treat as constant. And if you write down just the equation for the future value, to basically just change the indices. Xt plus 1 equals 0.75.
Ну, тогда 0,75 плюс 0,3.
Yeah.
1,5.
Yes. So it's something else. Yeah, I'm covering with myself, but yeah, there it is. Just plugging in the values as they are given, and in all the those calculations we use the fact that the white noise is 0 in expectation, right? And what moment is there the conditional expectation or unconditional expectation of the white noise term is 0, because the conditional expectations depend also on the correlatedness, and the white noises are not correlated. Weak or strict noises, they are not correlated with past values.
Vladimir Nikolaevich,
yes.
Can you please explain how do you get these results again?
Which ones?
First and second.
Okay, the first result is something that we covered some time ago. This is the okay. So this is our process, but really quickly and probably the last time. So that's it. The parameters of the white noise is not important now. The important thing is the zero expectation. So first what we notice is that the process is stationary, right? Well, weakly stationary, but that's what's important now. Because the coefficient, the autoregressive coefficient is less than 1 in absolute value. That's the rule for autoregressive of order 1 process. Then we know that the expectation is constant over time, and we can just find it. So this is just the definition of that future value according to the process. You just plug it in. The expectation is a linear operator, so you just can uncover it. Constants remain constants. You can take them out. White noise is zero in expectation and disappears. That's it. And what you have here is the expectation of a stationary process in the current period and in the past period, or in the future period. And since the process is stationary, these things are the same. And you can just derive it. That's it. This is what we did a couple lectures ago with stationary processes. This is how you find it. The other thing is when you want the conditional expectation. You know the current value, it's something. So basically you observe the process in the data, or you, for example, you estimated this process to or fit your model, your ARMA models to some data, and this is the model that you decided to work with. It doesn't matter where you get it from, or it is just a theoretical process that you analyze. And now you're interested in what is the future value of X given that you know this information about. This is the nature of prediction problem. What is the future value, or what can we expect in the future from this process? Given that currently we observe that something happened. So this is what we currently observe. We'll probably also observe stuff that happened before, but this is what is important because this is the most recent known information, and the process crucially depends only on the previous known value. If it was a more complicated model, we also would be interested in knowing something more about what was happened 2 periods ago, 3 periods ago, and so on. But now to find it out, you just, well, first of all, of course, you plug in the equation for the future value the same way as before. But the expectation remains conditional. And now since in conditional, whatever is in the condition you treat as known, as constant. So now this thing is also a constant. So you don't have to find or know this expectation to break this. Well, but this thing is conditionally or unconditionally is still zero. Done. That's it. This is 0.3. So the result is a little bit different than unconditional. So conditional expectation, well, they might be different, of course. Conditional expectation, unconditional expectation, those are just two characteristics of this particular future value. When you account for some information, when you don't account for some information that you know. Oh. Then the next natural question would be, what should the forecast of that future value be? What do you think? Again, the situation is like that. Okay, so we are currently in time period t. What
Ну,
the forecast would be?
ну, я могу предположить, что это будет 1.05 плюс какое-то случайное значение из вот распределения big white noise.
Yeah, well, yeah, it's a legit assumption or something. The question is actually tricky at this point because we don't know what the forecast is. Generally, forecast or prediction, that would be the same in this case. Forecast of a future value or prediction of an unknown value is some estimate of the unknown value of a process or a random variable in some particular circumstances. So in this case, the estimate of the future value that it has not been yet realized or that is not known yet. So we are going for an estimated, yeah, estimates, they usually depend on data and naturally they are random variables because they depend on random data. But when we calculate them, they are just numbers. So they don't include unrealized random variables in them. So it must be something that can be calculated from the data probably, or from what we know. So there are several options suggested. So there's suggestion of 1.2, then 1.05 plus something. Anything else?
Ну, может, просто 1.05.
Yeah, just one. Yeah, that would be more reasonable than plus something because, well, if plus something, then plus what? Yeah, just 105 because this was the conditional expectation. What's wrong with just expectation? And where did you get this from, I wonder? So yeah, previous value, this is kind of like a naive prediction. So the last known value is 1.2 and the next, yeah, if it was a random walk, that we know that the future value is just the past value plus some random noise that is 0 on average. Yeah, but otherwise it is a strange suggestion for such prediction, but well, why not? Or such forecast. What about just 1? Is it a reasonable prediction? It is the expected value. We don't call expected values expected for nothing. We expect them to happen.
Ну, это можно, но мы тогда все данные имеющиеся не используем.
Yeah, well, it's better than this because we are using something really incorrect when we suggest this. Yeah, so there are different, so the message of this question is that there are different candidates for the predictions. And 1.2 is not really a good one because it does not correspond to anything that we know about the data. Yeah, we can sometimes suggest that the previous known value is the expected value in the future, but this should be relevant with the process that we observe. And our process that we observe or that we assume or something, we got it from somewhere. It doesn't matter. This is what we work with. Our X lives according to this process, this model, whatever this now. So this is what we think about as the data generation process. And it's only 1/4 of the past value plus some constant, and it's not gonna be probably again 1.2. It might be because there is also random component, but well, intuitively, 1.2 for this kind of process should be not a good forecast. But both the unconditional expectation and conditional expectations are quite reasonable. Why not? No? What is the difference between those two values as forecasts of the future values is, and in this case, actually, this, you see, there's a new notion. This is a short way to write down the conditional expectation. Whenever you see, what is going on? Whenever you see this, this is the same as the conditional expectation given everything that we know up to time point t. So not just the last known value, but everything that we know. But in this case, the last known value of xt and the everything or all the information that is known is the same, because we don't need anything else to know everything about the process that is important up to the moment t. So this is just the short way to write down that the expectation is conditional. It's small index t, so pay attention to them. Don't confuse them with just unconditional. Now, the question now is, what is the difference between those forecasts, and why should we say that one forecast is better, why one might not be so good? How should we like distinguish between different forecasts? Any ideas? There is already some hint that I was covering with myself. You already know all the information to be able to answer to that question. So there's a unknown value that is yet to be realized. We don't know the actual value of that something. So we estimate it from what we know. How do we even say if the estimate is good or not? When these courses, this course of time series and econometrics 1 were going along together, it was maybe a difficult question. Now, when you've already finished probability, statistics, more statistics, and econometrics 1, this question should not be difficult at all.
Это
There's
что-то просто...
something unknown, we estimated. How do we even start thinking about whether the estimate is good or not?
Ну, есть разные критерии, там состоятельность условно какая-нибудь.
Yeah,
Вот это все.
something else. Yes. Also, how do we compare two estimates between each other? Well, it would be nice if we knew the actual value. For example, we could have waited, right, for this thing to happen, see what it actually is, and then see, okay, so one of those were closer, one of that was not closer. So one clearly is better, but can we say in advance which one is going to be better from the theoretical point of view? Because these are some expectations that describe our process. Again, so that's the process. And we have two estimates for the future value. This is 1. This is 2. Yeah, there's also other things like 1.2, for example, but this one accounts for the information that we know. about it. The first one doesn't. What's the forecast error of those things? The forecast error is the difference between the actual value and the predicted value. Or, well, I don't think that you used ever this kind of terminology in econometrics, but you always consider this thing. So we estimated the coefficients beta of the regression. Let's consider the difference between the estimated values and the actual values, right? So this you saw a lot and then did stuff with it. I believe that when you, if you recall that word cloud that I asked you to do in the very first lecture, and there was this huge word pain associated with econometrics, I believe that this pain in most of part of it originates in this thing because of those stuff. Something. So making those comparisons, we can judge about the quality of estimates and derive something. So something close is going to happen here. Not so terrible, but well, wait for it. So the forecast error, by definition, what the forecast error is the difference between the actual value, which is a random variable, and the estimated. Well, in this case, also one, because there are different predictions. If you just plug it in, what can we say about this error? And if we are going to plug in the same thing but with the other prediction. So these are two prediction errors of two different predictions, so two different forecasts. Can we say from just looking at those prediction errors or forecast errors, which prediction is better and why? Just
Может быть, та, у
intuitively.
которой мат ожидания 0?
Well, they both have kind of zero expectation, so they are both unbiased. But why? They are unbiased, but in different sense. It is strange to see that they are only different, yeah, by this 0.05 term here, but really they are both unbiased, because when you try to find the conditional expectation or the expectation of it, the first one should be taken unconditionally, and the other one should be taken conditionally, because this is how the expectations, this is how the predictions were found. And just by construction of what the prediction error is, we know that the not the prediction error, but what the forecasted value is. This was the expectation, so this will of course be 0. And same way, that should be t plus 1 here everywhere, because this is for the period t plus 1. Also is going to be 0 because of this. So they are both unbiased given the information that they used to, yeah. So the suggestion is that the best is the one whose error is less, but the error is also the error of prediction of the forecast error. This is what it stands as. The FE stands for forecast error. Is a random variable itself. You cannot just say, so this is smaller than that one, because they are random. So then how do we compare? You already know that. Something about efficiency of estimates.
Что дисперсия одной оценки лучше другой?
Yes. So they are both unbiased. So this is already good. In this sense, this thing when we suggested that 1.2 could be like the previous known value, is even not zero, whatever you take it, conditionally or unconditionally. This is already a bad forecast because it's biased. There's a systematic error. And if you change it by a constant, this thing, it will be at least centered around the true value. So this is what we are looking for. Something that is, at least on expectation, is around good. And then there's also the question of variance. And one forecast error could have like nicer dispersion or less variance. So out of those two, which one has less variance? And again, the difference comes from the fact that this is unconditional, this one should be conditional. Same with variances. We're not going to find the exact variances, but just look at this. When you take things unconditionally, both of errors will include constants that are constants whatever we do. They don't matter. This is also a constant. Some constants, they don't matter for the variance, right? These constants are here only to account for the average level. So these are the different average levels, one conditional, one unconditional. These constants don't matter for variances because variances are not do not change when you shift the values by constant. This thing has the same variance whether conditionally or unconditionally. It's the same white noise term. It has, well, the variance of it is even given. It's 0.25 because the standard deviation is 1/2. What about these?
Во втором случае будет 0 дисперсия, потому что она константа.
Yes. In the second term, when you account for the information that the true value of the random variable in the past is something given, we know it. It is going to be cancelled out from the variance. The conditional variance is 0 of this thing. In the first case, when we don't account for the information and we have to deal with unconditional variances, this thing will also create variance according to the variance of the process. This is a stationary process. The xt is comes from a stationary process, so it is some reasonable value. We can find it. It is defined and can be well calculated, but well, still, this does not create any variance when you count it for conditionally. So, well, this is just the explanation why the conditional expectation is a preferred estimate or the preferred candidate for the prediction. So the last question is rather theoretical. We are not going to answer for it in every detail, but I already kind of pushed you to that answer, or at least to guess the answer. Is there any other forecast that minimizes the variance? So there's variance, whatever forecast we use, there's different variants of forecast error. So is there anything else? Can we suggest something else to predict the future value of our process to minimize that variance? Not just to be able to see that, okay, this variance is less than that one, but is there anything else? Well, you don't have to know the answer to that question, but there is the answer. So in general, there is a thing that minimizes the variance. You saw the same result that you just did not call the way the things as they are called, like forecast and so on, but you saw the result. The result, the prediction or the forecast that minimizes the variance of prediction prediction error or the forecasting is called the mean squared error. Sorry, just a second. Colors. the prediction that minimizes the variance of prediction error, or the forecast that minimizes the forecast error variance, is called the mean squared error optimal, because the variance is the mean squared error. Error is what the difference gives, and then when you take its squared and take mean of it, you take the value, you get the variance. This is the idea behind the term MSE, mean squared error optimal. And then we see one step ahead. One step ahead is because we use the information up to the point t, given that we know the last known value. In this case, this is what is important. If we had there another process, we could use also other information, but we only take the prediction of the next value. So this is one step ahead prediction, plus 1 to the current t. So there are two conditions. First, it must be conditionally unbiased. So the expectation of the forecast error is 0. This we get from the conditional expectation, actually. And it must minimize the variance of the prediction error. So this is the function of some function of the last known value, or all the information that is known up to the point t. And when you minimize this function, so this is what you get. So this is a strange, maybe a thing that you might not have seen in econometrics 1, but actually you saw, and you actually saw the result. So if you write down this problem in general for the example 1, and you are very welcome to try it on your own at home, just plug in instead of xt plus 1 the actual equation for xt plus 1 as function of xt and epsilon and coefficients, then plug here some unknown value like just x or z, whatever, and minimize according with it, but with the restriction that the expectation must be 0. Here I think it's typo, it must be conditional expectation, of course. Here it should be t, given the information. And as the result, well, you can guess already by now, because as the result, you are going to get exactly this. The expected value of xt plus 1, given that the past known value is 1.2, so 1.05. This is a general result. You can see the proof of this theorem in general. Well, this is something too complicated for our course, even though the proof is not very complicated, but it will take some time. But the result is quite general. The optimal predictions, optimal in mean squared error term. So the predictions that, or the forecasts that minimize the variances of the forecast errors and that keep the predictions or the forecasts unbiased, so that on average the error is 0. They are conditional expectations of the future value given the information that we know up to the moment, whatever we know, the most information that we know. So whatever information you have, if you account for that and take the conditional expectation, this would be the forecast that minimizes the variance. The intuition behind is that, well, when you take things conditionally on the information, you get rid of most uncertainty in your future forecast errors, because whatever you know, you treat as a constant, and it does not include create any uncertainty. This is the theoretical property. This is the theoretical justification of why we try to use conditional expectations as prediction values. And whenever we use it, remember that it is based on the idea of the predictions that minimizes the variance of the future prediction errors. In this case, there were in that example there were two candidates for the predictions. One is unconditional expected value, the other one was conditional expected value. They are both valid candidates for the prediction. Even the first one is also, in some sense, an optimal prediction. It is an optimal prediction for the future value when we don't have any information about what happened in the past. Because when we have no information about what happened in the past, the conditional expectations become unconditional, and this is what we get. As long as we have some information about the past, and we account for it to minimize the variance of the future prediction errors, we get something different. Well, the difference in numbers is not so high in this case because the process is somewhat like very stable and not with huge coefficients and so on, but still. Now, tomorrow we are going to discuss how those variances are derived, but now we don't have time for that. So this is the general terminology and the general result, how you see it, not just for one step ahead forecasts, but also for other forecasts. So optimal in mean squared error sense. So this is the MSE optimal, stands for mean squared error sense, optimal forecasts. The general result is that when you want to get an H periods ahead forecast, this doesn't only stand for one period ahead forecast, but also for further ahead forecasts. Given the available information at time t, the best in mean squared error sense prediction is the conditional expectation given that information. This is it. The H comes here, when the H periods in the future from the last known thing. That fancy IT stands here for all the information that is available to the time point t. In the previous example, it was just the past value. Imagine that in the previous example, we knew not the last known value, but something like what happened to the process only 3 periods ago, or like 5 periods ago, t minus 5, or t minus 4 in this case, 5 periods ago. Would this work still? Yes, it will still work, but the prediction would be, in terms of this result, the prediction would be 5 periods ahead. Even though now it's time period t, but we don't know what happened to the process for the last 5 periods, for example. And we still want to know the next future value. Why? Well, why not? It might happen. First of all, we still might be interested in predictions for the further future that is yet to come. Not necessarily one period ahead, but more periods ahead, or sometimes in real economic situations. For example, we observe, well, something like monthly data, but we can only get the actual data when the year is over. So the frequency of the data is monthly, and the model and the process is formulated for monthly data, but the predictions that we can draw only for like in monthly frequency, but for the values based on something that only happened more than a year ago or only last year. And for example, we are in the middle of the year now. We know the last values that came only last December, but nothing that happened in this in this year yet, because this is yet still to come at the end of the year. It happens, why not? Especially in Russian state statistics. Now a little bit about more general notation, what we say, how we read things, what things are, and how to formulate the results. When we want to forecast stuff, we say that there is a time process t. We still work with univariate things, so this is just a single valued at each point time t time process, but the notation will be exactly the same for multivariate things or for vector things. It doesn't matter now, but we are not going to consider them. So this is just a general process that we observe, and we say that this thing xt plus h hat given t, this is how we read it, given t or at time point t, is, this is just the notation for the conditional expectation of that future value of xt plus h given the information known by time period t. So these are all x hats are essentially conditional expectations. This is the information that we know. This is the time point for which we want the expectation. Hat means that this is not already that value from the process, but this is some estimate of the future unknown values. This is why the hat. And in general, so notice this important difference. We call this thing a dynamic forecast. Why dynamic? Because there is the desire to predict the unknown future, something that not yet happened, based on the previous information on the past. So this is why we call it the dynamic forecast. When h equals 1, and this is the only case, when h equals 1, this is what we call the static forecast. Why static? Well, because there's no difference, there's nothing unknown between those two time periods, t plus 1 and t. Nothing yet unknown between those two. So everything that is going to be predicted for t plus 1 period depends on that information that is already known. In this case, we can call it not only static forecast, but also static prediction. If you want to predict future for more than one period ahead, h more than 1, higher than 1, then we have to first predict the values for like the intermediate points for t plus 1, t plus 2, and so on, and then get to t plus h already based on the prediction done for the previous time points. That's why it's called dynamic. The corresponding difference between the actual value that is yet unknown and the estimate is called the corresponding forecast error. You just saw that. The notation that in the indices is the same. And then also something more general than we just saw, because we only saw the mean squared error, and in this case there's something else. Some scalar function that takes as argument the forecast error and sometimes also the values of the process itself, but it's not necessary. Often you will see just L as a function of forecast error. And that such that it has this the following properties. First of all, when the forecast error is 0, this function is 0, and whenever the forecast error is not 0, this function is positive. So this is what we call the loss function. This is basically shows how bad the prediction is based on the value of the forecast error as the random variable, of course, but the function is scalar. And then the expectation or the expected value of this loss function, that is what we call the quality of the forecast in terms of the loss function. What we saw just now before in the example, the loss function that we used in the first example did not take the values of the process itself to evaluate the quality of the prediction. It just used the value of the forecast error, and it was just this, the quadratic loss function, the most commonly used one and the most basic one. Then the quality of the forecasts is this by definition. And since the predictions that we can see that are unbiased, this is exactly the same as the variance. That's why the minimization of variance of forecast error is the same as the quadratic loss minimization. So this is just a change in notation. And now we can proceed with more about with forecasting from ARMA, and we'll go a little bit faster here now because we already established the ground for all of that. So consider a general autoregressive of order 1 process, and in this case the coefficient phi is something, and the question is very simple. What is one period ahead dynamic forecast? And what is the static forecast? In this case, this is a tricky question. So static forecast is the same as the dynamic forecast 1 period ahead. So this is about the same thing. When we are asked about static forecasts, this is the same as dynamic forecast for 1 period ahead. And then there's a question, what is 2 periods ahead forecast? And in this case, there's no clarification whether it's dynamic or static, because static prediction or static forecast cannot be done for 2 periods ahead. It can be done for 1 period ahead based on the information known by this point, but not 2 periods ahead or more. So for 1 period ahead dynamic forecast, we already know the conditional expectation of the future value is just that the constant time plus constant times the known value, and the expected value of the random component is 0 here, the only random that remains here when we take conditional expectations. And the one step ahead forecast is just this. Done. Dynamic or static. The next question is more. Tricky, because we are asked about what is the conditional expectation of the value of the process. Oh, sorry. 2 periods in advance, but based on the current information or on the time period t. So when you plug in, and this is what we do with the expectations. When you plug in the equation for the process 2 periods ahead, you get here something that we already know. First of all, the constants are treated the same way, and the expectation of the random noise is still 0, so I'm not even writing it here. But then, what about this? What is this?
Точечный прогноз для первого.
Yeah, so this is, yes, exactly. So this is why the forecasts for more than 1 period ahead are called dynamic also, because and why they are not static. Because when you derive the predictions for 2 periods in this case ahead, or naturally 3 periods ahead will require you to do that for 2 and so on, you get as a part of it the forecast for 1 period ahead, because this is an unknown random variable and you have to take it from somewhere, and this is the best way to predict it. And because our processes are linear, this is what you get in linearity. In non-linear processes, it might be not so easy, but generally the scheme is the same. So when you plug it in, I will move it somewhere, you get again mu and phi and done. You can open up the brackets and see what happens, but generally for autoregressive order or process of order 1, you can derive even the general prediction for like h periods ahead. It's not going to be so easy done by induction probably. For autoregressive processes of higher order, or even for ARMA processes, it's going to be not so nice. But still you can do it. If you cannot come up with the general, you can always done it recursively, because when you derive the process, the forecast for 2 periods ahead, you will need the predictions for 1 period ahead. and so on. If you need predictions for 5 periods ahead, you plug them in, you will get the necessity to derive the 4 periods ahead predictions, you derive them, you will need predictions for 3 periods ahead, and so on. And at some point, you will get to the known information. This is already a constant, that xt. Okay, this we're going to skip for the practice session, but the general idea you get. You just write down the xt plus h equation, plug it in, start substituting, you will get to lower and lower and lower time periods, and at some point you will get to the known information, and there will be something like that. Times some coefficients. Something very similar that to what we got when we were deriving the autocovariance functions. The idea was the same. And yeah, of course, since we are talking about the conditional expectation of future future h periods ahead forecast with something that happened only in time period t, and the process is linear, of course, this thing will be related to the autocovariance of that process. So this is another idea how to approach it, but we are not going to go there in our course, because that's not so important. The important thing is that we understand what is the principle behind the derivation, not all the formulas that exist there. And then the last and very important reasonable question: what happens with the forecast as h goes infinite? So what is the first? How would you call this type of forecast when we are asked about this? How would you interpret this value at all? Suggest a name. You know it, I'm sure. I'm getting unstable internet connection messages again. Can you hear me?
Да, не слышим.
Yes, thanks. So what would you call it? Something like the prediction of the future value in the infinite distant future. As economists, give it a name. Okay, this would be called the long run forecast. The long run forecast is something that is going to happen in the distant future, very, very distant future from what we know now. Any ideas what is going to happen with this value? As we go to the infinitely distant future, what's going to happen with conditional expectation of that future value?
Оно перестанет быть conditional.
Yeah, under some very important circumstances. But yes, so first of all, it will converge. It will converge to something that is unconditional, and you will be able to see it from this. If you write down the h periods ahead forecast, you will see that there will be something. The
Ну и
role of
получается
this
оно...
will diminish, and this coefficient in front of the current information will go to 0 as h is infinite, because the information is less and less and less and less relevant in the future. And then this thing, what does it remind you? As h.
Ну, это геометрическая прогрессия, она, соответственно. при условии стационарности она сойдет с просто
Yes,
числом.
so this is going to be 1 over, well, mu over 1 minus phi. And yeah, the important thing is here that if, this is it, if xt is stationary. So for stationary processes, the long-running forecasts just converge to their unconditional means. This is very natural thing. So the information that we know about it, so what happened at time period t, is less and less and less relevant, and unconditional expectation, conditional expectations become unconditional in that sense in the infinitely distant past or future. So they are just means or just expectations. This property is called mean reversion. The stationary process converge to mean to their to their unconditional means. There's another question here to derive the so-called error bands that would we leave out for the practical sessions or even for your projects, because this was described very well in the online course. We can derive them theoretically, but this is not so interesting. Basically, we want to find that a minimized variance of the prediction error and see how the prediction stays in, because the variance of the future forecast errors naturally expands, because there is more and more and more uncertainty between those two periods as h is larger. Because we still know only the information up to the period t, and what happened in t plus 1 we don't know, but the variance of it depends on the noise in that period t. But in period t plus 2, we still only know what happened in period t, and the error depends not only on the noise in period t plus 2, but also in what happened and what was uncertain, still is uncertain in period t plus 1. So the variance is increasing, increasing, and increasing, and the confidence interval, so what we call the error bands in this case, is expanding. In the online course, it's very well explained and illustrated with the nice pictures from eViews, so go there. We're going to skip this this example, maybe just discuss it very briefly, what are the ideas here, but the general thing is that, well, all the principles apply. You just have a more complicated process. So experiment with it yourself if you wish, and we are going to discuss something similar but with particular specific numbers in the practice session. The coefficients here are again constants. Now, by the information that we know up to the moment t, we are going to include not only the xt but also xt minus 1, because if we know xt but don't know xt minus 1, we are not going to be able to use all the known information about the process to derive the future expected values conditionally. So this is like naturally demanded by the way the process looks. So when we see the information up to moment t, we assume that everything that we need to know. So whatever happened by moment t is a constant. And all the other rules apply. So what is the general h periods ahead forecast? It is not so easy to derive it as in the case of the order 1 process, but it's still possible. It's the same principle. Then will mean reversion work here? Well, yes, of course it will, as long as the process is stationary. If it's not stationary, no, it won't. The long-running forecast will diverge. It will not exist. It will be either infinite, plus infinite, minus infinite, or even oscillating. So it's not going to be defined even in the infinity, but that's a very complicated case. No, but we can even judge about it, yes, from the previous question when you write down the formula for the h periods ahead forecasts and just find the limit as h is infinite. Same idea about the error bands, so look it up in the online course. This is important, but still we don't have time. And of course, look it up all for the general process ARMA PQ. This is the same idea exactly. We are going to discuss a problem tomorrow, like with particular numbers in the practice session, or maybe even not. But this is what you are going to do essentially in your project tasks. But then you will get to all the calculations done by your predict function or in your codes or whatever. So you don't have to derive them, of course, by hand, those predictions. Everything is done then, but the idea is exactly the same. You take the known information, you calculate the 1 period ahead forecast, from that you calculate 2 periods ahead forecast, and so on. And if your process is stationary, then you can also derive the unconditional expectation, and that would be the long run forecast. Okay, I see that I am going to delay you a little bit, but this is something that we need to discuss because this is going to help you with your project tasks. And following my comments and following the online course, you already started doing that, and that's good. So we are going to talk about it only very briefly. And this is already not about theoretical properties or theoretical properties of the processes. This is about working with data. So those were the theoretical principles behind the prediction, and now about what we did. So when we work with the data, this is what you did so far, or this is how you should have done so far in your time series projects with your actual data. You ran the preliminary analysis of the data. You chose some ARMA processes or ARMA models, sorry, that fit and pass the in-sample diagnostics that are not too high order. Residuals resemble white noise, and among those, there are maybe at least one or maybe few competitors that fit the data the best. And then you have to derive predictions and compare which predictions are better. And because we don't observe the actual values of the future process until it happened and until it's realized. And the theoretical properties of the predictions are always like that. You take a model, the conditional expectation based on that model is the best prediction derived from that model. But whether it's going to be actually good in real life data, we don't know. That depends on the real life data and how precise our estimations of the model are and what is the noise there and what is going to happen in the future, blah, blah. So there are a lot of things that keep distance between the theoretical best predictions and the actual best predictions that we need to use. Yeah, from each model we take the best that we can. That would be the conditional expectation or something else. But then we also validate our models how they actually predict when things happen, and we can compare the actual values that happen in real life with things that we predicted from the models. And based on that, we judge whether our models are relevant or not, and which ones we should use or which ones we should throw away and never remember about them again. So there is no unique answer to that. There is a huge field of forecasting. It's a little bit overlapping with time series analysis. It's a lot like comes away from the time series analysis. It's a different field inside the statistics or probability and other more general subjects in that area, but still it is related. So how should we come up with forecasting schemes to get better predictions? So machine learning is a lot based on that, on those ideas. Time series that deals with practical predictions also works with that. So these are the very basic ideas, and you must apply them in your project tasks to succeed. And in the future, if you deal with predictions, you are going in some way use one of those approaches, maybe a more advanced version of it, but still the basic idea is going to be exactly the same, I'm sure. So first of all, the most important rule here is that when you get the models that fit the data best, fits the data best, there's no guarantee that it is going to give you reasonable predictions. Not only that it's not guaranteed that it's going to give you the best predictions. There's not even there are no even guarantees that it's going to deliver reasonable predictions because of many reasons. One of them would be overfit, because if you overfit the noise that is in your data on your fitting sample, you are going to get that same noise predicted in the future, and it's not going to happen. So that will only noise up your future error of predictions. And we need to observe the actual quality of the predictions to judge about the quality of the models. The general scheme is like this: you divide this is what you already did. You divide your sample into fitting, validation, and testing. Sometimes it's just two of them, but lately and well, recently, it's almost never already used because there's quite enough data to do all three of those stages in all the modeling. So fitting is where is the biggest portion of the data, but still quite recent, where you estimate your models and do the in-sample validation. So throw away the models that are definitely irrelevant. Then you evaluate the quality of predictions on the validation samples. So basically you predict based on your fitting data, you predict for the validation period to diagnose the predictions, and then you choose the best model, and then also like revalidate or not cross-validate, revalidate or test it on the testing sample, just the latest portion, the most recent one, just to make sure that it still makes sense, and come to the conclusion that yeah, okay, so this is the best that we can do based on that data and those models and so on. And when you get to the testing sample, this is what you decide, okay, so this is what we did, this is where we can get, and based on that, you get more insights about your data and also the applicability of this approach and the models to this data, and maybe know more about what is going on. So this is why when you see, and many of you comment already to me that we don't get reasonable predictions, can we please change something, can we change the data? Again, no, you cannot change the data because this is not how it works in real life. This is about real life application of yes, very simple models, but to real life prediction problem and actual data that are quite reasonable for many purposes potentially. So this is what you should do. You have to get to this point and decide, or not decide, to make the conclusions about how reasonable these models and these methods are to predict this particular data in this situation. And the situation is crappy everywhere now in the world. If you think that you have the only unique data that were screwed up by the year 2020, well, big surprise. No, it isn't. So deal with it as the rest of the world is doing. You are like 1 year to become the professionals in that. So you have to be prepared. There's an empirical illustration to how we do that, and I'm going to go over it really quickly, and that's the last thing that we are going to do today. There's, you see, you don't see, I'm covering the number of the slides luckily, but we are somewhat like in the middle of the presentation, but most of it is just slides and tables. You can go over it yourself to study in more detail all the steps of what is done here. We're going to skip the essential analysis. Basically, this is already something that we saw. CO2 emissions, annual data in megatons in one of the African countries. There is a trend that is probably linear, probably exponential, probably quadratic, we don't know. So ideally, we would have to consider several alternative stationary transformations based maybe on our theoretical assumptions or about our essential knowledge about the nature of the growth. I would personally stop maybe with log differences as stationary transformation, because the trend resembles something exponential, but second differences might also be good. But in this example, I proceed only with log diffs. So this is just narrows down the predictions that we do. This is the log diffs that well, is assumed to be this, stationary enough to proceed. There is something happening in the beginning because, well, this is quite old data, many years ago. And for the future prediction, the decision to divide the data is the following. So the black portion, this is the too old, outdated data that I decided to throw away because it's too irrelevant already for the latest data here. The red portion is going to be used for fitting, green for validation, and blue for testing. There is no general rule about how to divide it, so I just divided it like this. The idea is that about 80% of the sample must go to fitting, and the rest is going to be divided somehow between validation and testing. This is when we lack data, and this is obviously one of the situations when we have not too much data points, too many data points, because the annual data for quite a long period of time, but not so long as even many of you have. If you had, if we had here higher frequency of the data, we could be very creative with how to divide the sample. For example, if the data were daily, we could use only maybe a few years to feed the data, then validate, test, then refeed the data on more recent data, and again revalidate, retest, and so on, and see even how the best predictions change as time progresses, and maybe something happened. And if a few years ago there were one models that were predicting the nearest future the best, now it's something a lot different, or maybe the best models were stable across time, even though the actual properties of the data changed. That is also a relevant outcome, relevant analysis. But in this case, no, just divide and yes, and conquer whatever you have. After the analysis that I skip here, so the in-sample analysis and diagnostics, the thing that we discussed last few times and you already did in your projects, I came up with several models that explain the dynamics of the data on the fitting sample. The weak white noise plus a constant, so this is basically ARMA 00, then ARMA 01 and ARMA 10 and ARMA 20, so just autoregressive processes. They are all a little bit different. The coefficients are close but different, and these are actual empirical values, so they are not simulated or anything, just applied to those data. Maybe rounded coefficients values, but only for the visual representation purposes. And then we prolong the data from the validation, from the testing, from the fitting sample, sorry, to validation. If you noticed on the graph, the transition between the fitting sample and the validation sample was 2007, I think, yes? So, yeah, 2008. So whatever starts in 2009 is already validation sample. This is the last portion of the data that we have as it is known, and these are the last fitted values of the of those three models. Whatever comes next is the prediction made to that validation sample dynamically. So based on this information known up to the time point 2008, we do the dynamic predictions for the period of validation sample. The prediction of the stationary process, of course, in this case, if we had several stationary transformations, that we would have to compare the predictions made for the actual data, not for the stationary transformed data. But in this case, there's only one transformation, one time series, so this is okay to analyze like this. The prediction, according to the weak white noise plus a constant, is of course a constant, because there's the expectation of constant plus weak white noise is always that constant without the weak white noise, which is 0 in expectation. So this is the value of that constant. Then from autoregressive process of order 1, see how it evolves quite quickly, because the coefficient of autoregressive process of order 1, if you noticed, was quite small here in absolute value. So it means that the values of these predictions are going to converge to the unconditional mean quite fast, because the value of that 1 minus this thing is going to be close to 1. So it is something different in the first period, then there's something different in the second period ahead, and then it's the same. So basically already converged to the unconditional mean. And a similar picture, but slower convergence, but there is still convergence for the autoregressive order of autoregressive process of order 2. We don't see the convergence actually within this period because it's more complicated and it takes longer time. What we do next for this only validation period, so now we disregard these 2 points because this was still fitting period and leave only the period from 2009 to 2013. We evaluate the prediction errors. This is the difference between the actual values and the predicted values. And we combine them together to estimate the quality of the predictions. And in this case, I use as quality of predictions, I use the mean squared error. The classic well, sample variance in this case this is exactly mean squared error. So just you square up the forecast error in the sample, and you sum up and divide over the number of observations, which is just 5 in this case. And as you can see here, this criterion is minimized by the autoregressive process of order 1. So the autoregressive process of order 2 creates some dynamics. They're interesting. Maybe the predictions are not so boring, but the error is higher. The weak white noise plus a constant, or ARMA 00, is too simplified model. So it's too simple and far from the actual values on average. And this process is somewhere in between and gives the best prediction. Yeah, so next we just evaluate the actual predictions, and the well, yeah, I was looking for yeah, I thought there is a plot, but there is no. Okay, and the last question, and this is something that you are going to address tomorrow in the practice session and also in your project task, and this is the last slide that we are going to see here. We're not going to discuss it anymore because I already delayed you for a long time. I'm sorry for that, but this is the last time when we are going to see the prediction from linear processes in the lectures. So there are a lot of points that you can change, that we can change even in this example, but you can also change to make this scheme to work for your example. First of all, you can decide to throw away or not throw away some old data. You can decide how much data to leave for testing, how much for validation, how much for the yeah, for all those stages. Then we can decide which data to use as transformed data. So there might be even more models, not only those 3. We can also decide to include more models other than those 3 if there are more reasonable competitors there. Maybe higher order autoregressive processes, or a mixed order model instead of R2, ARMA 1.1. Why not? But I did not include it because it failed some criteria of in-sample analysis. We could have used dynamic forecasts. Here we use dynamic. We could have used static forecasts. That would be another approach and another forecasting scheme. We are going to discuss it tomorrow. And in some cases, in some projects, for some of you, the consideration of static forecasts instead of dynamic forecasts, even in the stage of validation and testing, is going to be the answer that will help you to choose better models for to answer to your questions. So there is no rule that if you are working with time series, you must use only dynamics forecasting schemes. No, you can also use static forecasts. And then we only compared the predictions in terms of the variance or the mean squared error, but we can also consider other quality criteria for predictions. So basically change the loss function. And that depends on the nature of the prediction problem. We are going to also talk about that tomorrow. Yeah. Well, the last point, the evaluation of the testing on the testing sample must come in the same criterion that we used in the validation. That's natural, but still, there are a lot of things that we can change. So please think about those things that you can change in this approach in your particular task, and maybe share your ideas with me. Okay, that's it for today. I'm sorry for this delay. This all because of the quizzes. So if you have any questions now, please ask. If not, then you are free to go. And see you tomorrow.
Владимир Николаевич,
Yes.
у меня очень много вопросов.
Okay.